Hi everyone, in this video we are going to cover section 6.2, determining volumes by slicing, and we begin the section by trying to understand what is meant by a solid of revolution. Alright, so in the last section and earlier in chapter 5, we talked about the area under a curve. That's what we find when we evaluate definite integrals, right? So the cumbersome approach to finding the area under a curve is to actually divide the region up into a whole bunch of rectangles, right? That's how we were initially introduced to this. Find their area and then add them up as you move through the region. That is what you are doing when you evaluate a definite integral. That's what the calculus is doing. And the height of each of these rectangles, remember, is the function value at that point, right? We have the x and the f of x. The width of each rectangle is the delta x that we saw previously. All right, so now we are going to take this one step further, shortly introduce a formula that will allow us to take this region in the xy plane and revolve it, spin it around the xy plane. And you can kind of see that process, that development of revolving the region around the xy plane, right? And so we're spinning this function around, ultimately producing what is called a solid of revolution. All right, and we're still going to talk about that little rectangle inside of the region. That's a poorly drawn one. That rectangular cross section inside of the region, because maybe you can kind of try to picture what a really thin rectangle would look like when it's spun around the x-axis. I'll have a name for that a little bit later. Okay, but this is that's what we're doing in this section. In introducing the formula that I will shortly, we will find ultimately the volume of this shape. So volumes, not using volume formulas like V equals pi r squared h for a cylinder, but volumes of surface, or volumes of objects produced by functions and then spun around an axis. Pretty cool stuff. Before I get to the formal formula, we are going to go through an example first, and then I'll give you the straight up formula. But we'll kind of see where that comes from through this example. So we're given a function f of x equals x squared minus 4x plus 5, and the bounds are from x equals 1 to x equals 4. And I have the graph there for you in the region highlighted. Okay, so our function is a parabola. The y-intercept is up here at 5. Okay, and this is the region that we are. This is the region that we are looking at, and we are going to revolve that region around the x-axis. And fortunately, if you have trouble picturing these things, I have it here. Let me zoom in on the revolved region, and it makes this funky looking shape, almost like maybe a megaphone that someone might use to make their voice louder. But that's the three-dimensional region that we are ultimately going to find the volume of. All right, so now I'm going to go back and forth for just a moment here. And in our two-dimensional region, right, we want to draw that rectangle in, because that is ultimately, understanding that rectangle is where our formula for the integral comes from, right? That if I were just finding the area of the region, it would be the integral from 1 to 4 of our function f of x dx. That's what we have done previously. Okay, but now the new step, the new process is to take that rectangular cross section, that slice here, and kind of visualize what it looks like as it spins around our region. Okay, and what we end up with is this almost like well, it's a circle, but it's a really, really thin disk, just like our rectangle is a really, really thin rectangle, right? We take the limit as n approaches infinity. So there's a lot of them, and they're all really thin. This is a really, really thin disk that I'm not very good at drawing, but I can visualize and conceptualize what that disk might look like as it spins around the x-axis. Okay, and so what we're going to do here to set up our integral, to say we want to find the volume, okay, we have the integral from 1 to 4. That should have hopefully been without question. We were given the bounds at the beginning of the problem. And so instead of in 2 dimensions adding rectangular slices as you move through the region, what are we adding up now? Well, they're these circular discs, and I'll talk about the disc method on the next slide, but we're adding these circular discs up as we go through the region, right? And that's really an area, well, instead of a rectangle, the area of a disc, or a circle in this case. I'll write it off to the left here. A equals pi r squared. So we're adding up a bunch of circles instead of rectangles. Really, really thin circles. Well, they'd be discs because a circle is flat, but they're discs because they have a little bit of width to them. All right, and so the height of the disc or the circle is the function. So really, what we're going to plug in, what we're going to substitute in to our integral is pi times the function squared dx. And the function was x squared minus 4x plus 5. Okay, so that is our integral that will give us the volume of this bullhorn, if you will. So we now need to evaluate this integral. And that's going to be the challenging part moving forward, is figuring out how to set up the correct integral, because hopefully now you're getting better at evaluating them. So the challenge is to set up using the new content of the section. We can factor our pi out. I'm not taking the antiderivative yet because I have to deal with this squared. We're going to expand out that trinomial inside of the parentheses. And that gives us, let's see, x to the 4th minus 8x cubed plus 26x squared minus 40x plus 25, and then dx. Okay, so I got that by multiplying this trinomial by itself and just making sure I was careful in distributing all of the terms to each other. So then we take the antiderivative. So x to the, I don't want to write it like that, x to the 5th over 5 minus 8x to the 4th over 4, 26x cubed over 3, 40x squared over 2, 25x, and all that gets evaluated over the bounds from 1 to 4. Now it's an arithmetic question. You make sure you type it into your calculator super carefully, and it should give you 78 over 5 times that pi at the beginning. And what that 78 pi over 5 represents is the volume of that region. So that would be in cubic units. It's the volume of all the stuff inside of that blowhorn. So summarizing and now giving you the formal statement for the disk method, right? If I have a parabola in this case, or any function, we can draw our thin rectangle underneath that function. When it spins around, when it revolves around the x-axis, we produce a disk, and you add them all up using integration, and it's called the disk method. Okay, so we have the bounds of our integral. We'll either be given them or have to figure them out. We'll be given a function always, and our volume is the integral from a to b of pi times the function squared dx. And the way that, where that comes from, that is a equals pi r squared. The radius of the disk of the circle is where the function is the height of the function at that point. So that's why it's pi times f of x squared. Let's do one more example before moving on to the next part of the section. We have the disk method. Our function is the square root of x, and our bounds are from 1 to 4. Now I happen to know what the square root function looks like, and it is this. Here's my square root function. I know the square root of 1 is 1, and the square root of 4 is 2. So here is the region that we're looking at in 2 dimensions. All right, but what we're doing in this problem is we are revolving that region around the x-axis. Okay, producing, in this case, I think it would kind of look like a bowl, but it would be a bowl that would be terrible at holding things because it would just fall over. So a bowl with a very rounded bottom. Okay, so let me use a different color to try and make this look all three-dimensional. So we're revolving around the x-axis like that, and my Actually, I'll draw a little rectangle in here so we can visualize that disk spinning around the x-axis also. Again, my drawing skills are not quite up to snuff, but hopefully you get the idea. OpenStax has a lot of these drawn out for you as well. Okay. Ultimately, plugging into the integral is more direct in this one. We have v equals, using the formula, pi times the integral, our bounds are given to us, 1 to 4. Our function is radical x squared dx. So to simplify this one first, pi, integral from 1 to 4. Do the squaring before you take any antiderivatives. The square root and the squared cancel each other out, so it's just x dx. So we have pi times x squared over 2, evaluated from 1 to 4. And then we can take pi times 4 squared over 2 minus 1 squared over 2, giving us, let's see, 4 squared is 16, minus 1 is 15 halves pi, 15 pi over 2. Okay, and that is the volume of that weird-looking bowl that I tried to draw over there. Now we can also revolve our functions around the y-axis. So pause if you want to read the rule for this disk method. Okay, but what ends up happening is we need to integrate with respect to y. So let's say that my function, let's say it does something like that. Here's my y, or my, it's x equals g of y. Sorry for the messiness there. So that is my function. And I want to spin it, revolve it around the y-axis. Okay, so the region in my picture that I'm drawing here is right there, and we're spinning it around. So those rectangular cross sections, we would add them up the y-axis as it spins around. Those disks add up the y-axis. So just when we're revolving disks around the y, everything needs to be in terms of y. Okay, the bounds in terms of y and the function in terms of y. And so for our example here, again, pause if you want to read it in its entirety. We have a function already written in terms of y. G of y equals the square root of 4 minus y. And I'll just draw a quick sketch of what that looks like. This is 2. This is 4 up here. And the function does one of these. It comes down like that. And we're revolving that around the y-axis. Okay, so we need to integrate with respect to y. Our rectangles get added up vertically up the y-axis. So our volume formula looks like this. Pi times the integral. Now, what are the bounds? That rectangle would start at 0 and go up to 4. So 0 to 4. And now it's g of y, so our function in terms of y, square root 4 minus y squared dy. So if I had been given the function in terms of x, I wasn't, but if I had been, I would have needed to solve it for x. So it would be writing x in terms of y instead of the other way around. But we were lucky. This one, they already gave it solved for x. All right, so let's simplify, Integral 0 to 4. Square root and squared cancel each other out. We're left with 4 minus y dy. And then antiderivative, y squared over 2, evaluated from 0 up to 4. And then we're going to have pi times 16 minus 16 over 2 for the top bound and 0 for the bottom bound. And so we're going to end up with 8 pi cubic units. And I didn't even draw this one in 3 dimensions, but again, in OpenStax, it's in 3 dimensions. This looks like a bowl opening downward when you have it in 3 dimensions. But we have the volume is 8 pi cubic units. And now the last piece to this section is called the washer method, but really it's not anything new. It's just a disk with a hole in it. Okay, so this is the same method to my mind. We're going to be given 2 functions. So if I have a function f of x and another function, I'll change colors, and this guy is g of x, and I want to revolve this region. Let's see, I'll draw it in red. I want to revolve this region in red about the x-axis, okay, we no longer make a disk. It ends up being a disk with a hole in it. And if I struggled with drawing discs, I'm going to struggle even more with trying to draw washers. So let's give it a go, though. All right. So let's change to white. Here is my rectangular slice, and that is revolving about the x-axis, and it's not going too bad. Looks like a donut. That's kind of what I was going for. It's called a washer. And there's my rectangular cross section. Poorly drawn. Go to OpenStax. They do a much better job of representing these visually. Okay, the difference in what we do, and so that washer gets added up through the region as we evaluate our integral. What's different about the process with the washer method is instead of just one function, we have a top function and a bottom function. Okay, so we have to account for which one is on top. That goes first. And then we take pi times f of x squared minus g of x squared. So it's the outer radius minus the inner squared. My outer radius squared minus the inner radius squared. And make sure you square each function individually first. Super important that you do that first. It's not the whole quantity squared. It's each function individually squared. All right, let's look at an example and see how this one works. So our functions are y equals x, or f of x equals x, and g of x equals 1 over x over the bounds from 1 to 4. Our y equals x function just is our 45-degree line, like that. F of x is equal to x, and f of x equals 1 over x. That guy, let's see, that function I'll draw in green. That has a branch that does one of these. There we go. All right, I didn't label my axes. I might have missed that on some other problems too. This is my y-axis. Okay, so that's the graph. I'll add a scale on that will help too. They both intersect at the point 1, 1. Okay, hopefully you can see how if you plug 1 into both functions, you do get the same y coordinate. And they tell me that that's the start to my interval also. And then the interval ends at 4. So we're going from 1 up to 4. And here is our region in question. But that region is getting revolved, spun around the x-axis. Go to OpenStax for the visual of the revolution. I'm not going to try to draw it. All right, but I can set up the integral. V equals pi, has to be there every time, times the integral from 1 to 4. Those are the given bounds. They were nice and gave us the bounds. And then top function squared minus bottom function squared dx. The blue line is on top, so that's x, and then the 1 over x is on the bottom. I'm going to write it as x to the negative 1. Actually, no, I'm not going to write it as x to the negative 1. I'm going to write it as 1 over x, because that one needs to stand out. This one needs to yell at you. I'm going to draw a 3D exclamation point, because that function is yelling at me, making me remember not to use the power rule. Okay, when you go to do your antiderivative, which I can do now, there's not much to simplify with x squared. Pi times x cubed over 3 minus, oh, but it's squared. All of that I was talking about before doesn't matter. Rather than go back in my video and delete it, which I could, this stood out to me because the antiderivative is the natural log of x. But when I was talking before, and I think there's value in seeing that clarity now, when I square it, it's not going to have that same antiderivative. This is x to the negative 2. 1 over x squared is x to the negative 2. And for that antiderivative, I use my power rule on x to the minus 1 over minus 1. All that gets evaluated over the bounds from 1 to 4. If you need to go back in the video to hear that again, that explanation again, go for it. All right, so I'll simplify the minus negative there, becomes addition, and then we substitute in our bounds. So we have pi times 4 cubed over 3 plus 1 over 4. So I dropped that x back into the denominator. And then minus the bottom bound, 1 cubed is 1 over 3 plus 1 over 1 is just going to be 1. Simplify all of that arithmetic, and you find that v equals, let's see, we get 81 pi over 4, and that again would be cubic units. Okay, if you're not writing the units with these answers, that's okay, unless it's like a real application problem. Most of these, it's okay to leave off the units. All right, so that's the volume of that region when it's spun around, revolved around the x-axis. All right, hopefully that helps you work through some of the homework questions. If you do get stuck on any, please reach out, let me know. Thank you very much for listening, and have a wonderful day.